All right, welcome back everybody to another video of Kalman filter theory and applications. We're starting a brand new playlist. This is going to be the first video of that playlist. So this playlist is about state space concepts. Okay, as you know, if you've been following the previous playlists, we had some on understanding the equations at a high level. Then we had another one on taking those equations apart. And now we're going to drill down even further on the state space concept. There's going to be approximately 8 videos in this playlist. So let's get started. So the topics for today are dynamic systems, the concept of state space, and in a future video, the next one, we'll do deriving the state space models from differential equations. We'll give you examples of differential equations. And then we'll do another video on deriving state space models from difference equations, along with examples, of course. Then we'll focus a whole video on just a state transition matrix, which is a very important topic. And then we'll talk about various kinds of state space modeling diagrams, block diagrams, signal flow graphs, and so forth. And then we'll conclude the playlist with some state space modeling in Python. All right, so now we're going to talk about the concept of state space. So the time-dependent behavior of a smoothly changing physical system is often modeled analytically by differential equations. These are called dynamic systems or dynamical systems. They are typically smooth processes. In other words, the equations and the functions that describe these things are continuous and differentiable, and they're functions of time. So smooth means continuous and differentiable. Newton's laws of motion are a good example of this. The first two laws assert what generally happens when a body is subjected to a force. Whenever a net force acts on a body, the body's velocity will change. That is, it will accelerate or decelerate. That's the first law. And then its acceleration will actually be directly proportional quantitatively to the applied force, and the acceleration will be inversely proportional to the mass of the body that is being accelerated. So this is the famous F equals ma, or written in terms of acceleration as the output variable, a equals f over m. So that means that if you keep the body constant, it will exhibit a small acceleration when subjected to a small force and a larger acceleration when subjected to a larger force. And likewise, under the same constant force, large bodies will exhibit a small acceleration, while small bodies will exhibit a larger acceleration. That's the inverse effect of the mass. So in Newton's second law, F is the resultant force, and it's a vector that acts on the mass m to produce the acceleration. In mathematical notation, we can write this as F equals ma, or m times v dot being the acceleration, the derivative of velocity with respect to time, or written in a different way, m times dv over dt, or m times d, the second derivative of y with respect to time, which can also be written as my double dot. We'll talk about the notation in a minute. Since acceleration is the second derivative, we often get from Newton's second law second order differential equations. The solution is sometimes called the output of the dynamical system. The resultant force is the vector sum of all the forces acting on the body, both internal coupling forces and external input forces. Little aside about notation. In mathematics, one often sees y as a function of x. Y equals f of x. In physics, however, the variable r, which is a function of time, is often used for vector displacement with coordinates being x of t, y of t, and z of t. In engineering work, the variable x is often used as the vector state variable. And in dynamic systems and control theory specifically, y is generally considered to be the output function of time t. Hence our use of the symbols y of t, dy, dt, and so forth. Also common in engineering use is the variable u, which stands for the external input, often a control function in control engineering. In these slides, we are going to mostly use standard engineering notation. Also, be advised that our notation does not distinguish in any way between vectors and scalars. We do distinguish between vectors and scalars, of course, but the notation does not. So we're not going to use bold-faced font for vectors, nor are we going to put little arrows on top of the vectors to indicate that they are vectors. So let's talk about internal versus external forces. Which forces are considered internal to the system and which are considered to be external to the system depends on how you draw the system boundary. So it's somewhat a subjective choice, and depends on what you're interested in. The simple harmonic oscillator has one internal force determining the system behavior, F equals minus ky. The spring itself is often considered to be a massless part of the system. More complicated oscillators may also include internal frictional forces or external driving forces. Internal forces are not generally viewed as inputs. External forces, when they are present, are typically time-dependent forcing functions. So for example, you'll see here in this equation a second order equation with the variable y on the left, and on the right the function is only a function of time. Most general second order equations for mechanical systems of this type look like this. Y double dot equals 1 over m times the forcing function, which is a function of y, y dot, and often t. Now, if it can be expressed, if f can be expressed as the sum of two other components, f1 and f2, f1 being a function of y and y dot, and f2 being a function of t, then we can rewrite this in an input-output form so that the output is on the left-hand side and the input is on the right-hand side. Note that the left-hand side is a function only of y and its derivatives, while the right-hand side is a function of time only. Okay, mechanical systems like a moving idealized particle have only three simultaneous translational attributes: position, velocity, and acceleration. And if we're talking about rigid bodies, then we also have some rotational or orientation parameters. Newton tells us that translational acceleration is often a function of position, velocity, and perhaps time. And there are analogous relations for rotational quantities as well. A force that acts on a system as a function of time only is often considered as an external forcing function, like we saw on the last slide. That is, a true input to the system. Thus, we can often think of position and velocity and their rotational counterparts, perhaps, as the primary state variables of interest in mechanical systems. Right, the concept of state involves, in some sense, the instantaneous internal arrangements and relationships of a system's components and their attributes. In practical situations, the state variables may simply just represent attributes of the system that we need to know about. Also, intuitively, state variables are usually naturally coupled with each other in some sense. This is obvious when the state variables are derived from a single differential equation in which all the quantities are derivatives of a single variable, the output variable. Now, we're going to talk about state as the initial conditions for a differential equation. Here's a quote from Rudolf Kallmann. How is a dynamical system linear or nonlinear described? The fundamental concept is the notion of the state. By this is meant, intuitively, some quantitative information, a set of numbers, a function, etc., which is the least amount of data one has to know about the past behavior of the system in order to predict its future behavior. To determine the behavior of a deterministic system at any future time, we must have some knowledge of three different things. One, we need some equations governing the system dynamics. In other words, a system model. We must also know what the control function or external forcing function is, if any. But then always we need to know what the initial conditions are. We cannot solve the differential equation for the future state of the system unless we know what the state is at the beginning. But the initial conditions for an nth order continuous dynamic system are simply the values of its first n derivatives at the initial time. The nth order derivative is given essentially by the differential equation itself. At any point in time, we can think of instantaneous values of the first n derivatives as initial conditions for all future dynamic evolution. So the first n derivatives are the 0th, first, and so forth up to the n minus first derivative of the output function y. These values capture the state of the dynamic system at any time after the time of the initial conditions. The concept of state is also encoded in the Taylor series of a function. Here's Taylor's theorem. If you have a function y and it has derivatives of all orders near t naught, then its value at any time t near t naught can be determined from the values of its derivatives at t naught. So here's the equation for that. Y at any time t is equal to whatever y was at t naught plus whatever the value of the derivative of y was at t naught times the quantity t minus t naught plus 1 over 2 factorial y double dot at t naught times the square of the quantity t minus t naught, and so forth. Now this might be an infinite series, or it might drop off to 0 after some point, or gets negligibly small. So in other words, the value of the function at any point near t naught is completely determined by its value at t naught and the values of all of its derivatives at t naught. Note that this works for some time points in the past as well as those in the future, provided they are sufficiently close to t naught. In the language of dynamic systems, the quantity delta t equals, by definition, t minus t naught. If that's greater than 0, it's simply the time that has elapsed since the initial time t naught. If you're worried about going into the past, then it would be negative. Thus, if you have knowledge of the state at time t naught, that is, if you know the values of all the possibly infinitely many derivatives, then you can determine the value of the function at any later time sufficiently close to t naught. This is because all of the dynamic information is contained in the derivatives. If y of t is smooth, each of its derivatives can also be expressed as a Taylor series. So if we change our notation slightly and use the capital D for the differential operator, the lowercase t, or the subscript t for the variable that we're differentiating against, and the superscript as the order of the derivative, then your Taylor series looks like this. But we can do that for the second derivative, the third derivative, the fourth, and so on, right? So where does that take us? Well, we can put all this into a vector matrix form like this. There you can see in the first row, it's just y of t being expressed as a normal Taylor series up to a point. This is just an approximation up to the n minus 1, order n minus 1. But you can do the same with the first derivative and the second derivative and so on. So you can put all this together into a vector matrix form. And you can see then how the state would evolve with time given this Taylor matrix. Notice that equation 4 is only an approximation. However, it's useful in evaluating the accuracy of a linear approximation to a nonlinear system. Taylor series are valid even for any smooth function, whether it's linear or not. But it does have to be a smooth function. It helps us to assess the accuracy of the time extrapolation provided the state transition matrix provided by the state transition matrix, since the above matrix Taylor series approximation is in fact an extrapolation. So we can use the Taylor series to kind of measure the accuracy of the state transition matrix, which we will talk about much later. The order of the approximation depends on the size of delta t, of course. If we take something that's a little further away from t naught, then we're going to need more derivatives to get all the information we need. We'll have more on this later when we drill down on the state transition matrix. Okay, so where are we? We reviewed the basic concept of state. We've discussed the difference between internal and external inputs. We've indicated how the notion of state is connected with initial conditions and, most importantly, derivatives. And then we've examined the connection with the Taylor series expansion of the output variable. So what's next? In the next video, we're going to show how the state variables in equations can be derived from differential equations. And here's a reminder that there are plenty of Python scripts out there on the internet. And that'll do it for today. Thank you for watching. We'll see you in the next video.